Okay, so here's where we were last time. We were talking about iterated integrals. Iterated integrals were our answer to I hit the wrong button. Our answer to a particular question, namely how to compute the volume under a graph. Right? You know, given the volume under a graph, we've got this sort of a volume we're looking at here. Big picture idea is we were going to slice it up, and then we realized that those cross-sectional areas are themselves integrals, and we find ourselves doing integrals of integrals. Okay, so thus the term iterated integral. Okay, and we did an example, talked through the little detailed bevels there, that you got to be careful to remember that the inside integral, when you see the outside variable in the inside integral, it's to be treated as a constant because it is literally constant for the purposes of that integral. Okay, and then we talked about how you can switch the order of the differentials, and only while we are here considering purely and only rectangular domains is it the case that you can just kind of switch the bounds like this. It's a really convenient little bit of luck for rectangular domains. Okay, that bad news is going to change when we start looking at different shaped domains. Okay, so I am going to pose a question. When we were doing single variable calculus, we considered first area under a graph, right? Kind of analogous to the volume under a graph question we're looking at here. And we wrote down a certain expression, and we got lucky that, hey, that exact expression that we wrote down for area under a graph, the exact same thing allows us to make a very reasonable case for the mass of a one-dimensional metal rod along the x-axis, or any of a number of other applications that involve chopping up some other quantity, right? Not area, right? Some other quantity, and the exact same expression works. So it would seem reasonable. Emphasis on seem, right? So fingers crossed, with a hopeful point of view, we would hope that if we want to compute the amount of mass in a rectangular sheet, not the volume sitting over a rectangle, but the mass contained inside of a rectangle, hey, maybe the same kind of formula should work where we had used height for our integrand in the volume question. Maybe we would use mass per unit area in the mass question. Fingers crossed. But maybe this will work, right? Well, as an argument, and keep in mind, in this class, it's very important. Y'all have heard me say this a million times. You're going to hear it a million more. This class isn't about the answer. It's about the reasoning process, right? As an argument, as a piece of reasoning, this, I'm sorry to say, does not allow us to compute mass. And here's why. Let's kind of break down. We'll go back to the volume argument first. And one of our big ideas was, if you look at this right here, right, then this was height and color choices. This was kind of length, if you will, and height times length. Well, it's conveniently something we already understand. It's area. Right, we use that very importantly in this argument. Now, I emphasize, this is not what the question was about. The question was about volume. Right? And yet area has made an appearance here. Conveniently, this product just happens to be something that we're already familiar with. And furthermore, this area, if you go back into the, where did we were doing stuff in the first place, that area is this area right here. It's the area of one of our little slices of our sort of whole cross-sectional area. And we make another argument here that relies on our existing intuition for how area works, namely that this total area is the sum of the slices of area. We can make that case because we understand area. We have intuition for area. We have experience with working with area. Okay, all right. So now let's look at where we find ourselves with, again, fingers crossed and hopeful that that the same kind of thing might, make some sort of analogous sense. And, well, let's see here. We've got here the integrand is mass per unit area. That was given. Mass per unit area. And we are multiplying again by a dx, which is a length. And, well, what is that? Mass per unit area times length. I don't know. It's not something that we have any previous familiarity with. This is now just a great big question mark. So, can I make an argument along the lines of what we did previously? Can I say that the amount of this mystery quantity, I guess I could call it mass per unit width, maybe, right? Whatever that means. This mystery quantity, can I make the claim that the whole is the sum of the parts along this cross-section? I don't know. I don't have any experience with this thing. I don't know what it is. I don't know how it behaves. So, no, I really can't make that argument. It doesn't make any sense. So, the punchline is we got lucky with this first calculation. Right? This first calculation, it just happened to be that I found myself in need of understanding of something that I, lucky break, happened to already understand. And then we did not happen to get so lucky down here. So the punchline I want to make is that this strategy that we have here, this idea that we're going to take volume and slice it up into areas and then make arguments about areas, this really only makes any sense as we're describing it here for volumes. Specifically, that's it. Right? And now let's talk about what are we actually going to need, right? When we're doing physics and engineering and stuff like that, are we just going to be sitting around computing volumes and that's it? Well, no, of course not. What do we do with single variable calculus? We compute areas, I guess, a little bit, but mostly with single variable calculus, you're computing mass and work and population and economic surplus and bazillions of different things that you can do with integrals. Those applications are why engineers and physicists care about integrals. It's not because you can compute area under a curve, right? And likewise, with what we're working on here, this volume question is kind of an incidental it's kind of geometrically satisfying, I suppose, but I'm going to need to be able to compute much, much more than this. I, in particular, am going to need to be able to compute the total mass as mass per unit area is distributed across a two-dimensional region. And this doesn't do it. All right, so, awkward. So, we're going to move on to a different attempt. I'm going to kind of segue into this different attempt by reminding you of some stuff from single variable calculus. Please do make sure that you're comfortable with the idea of a Riemann sum. Specifically, notice a Riemann sum is the definition of a single variable integral. And it's very important that this is the definition of a single variable integral. A lot of people think, come on, definitions are just for mathematicians, being uptight and, abstract, as mathematicians will do. That is not the point of this. Not even in a class like Math219. If you're interested in applications, if you're interested in computing, again, mass and population and economic surplus and da-da-da-da-da-da, stuff that you want to compute applications of, chopping that up into little pieces and adding up the answers on the little pieces is how you do that, right? The Riemann sum is the way that you connect single variable integrals to applications. This is not mathematicians just being uptight about, formalities. This is why integrals relate to problem solving. Very important point. Area under graph is, it's kind of nice and all, but, again, that's not really the point. A lot of people mistakenly think that if I, for example, want to compute mass, that I can just directly make a case for why that mass is the area under a certain curve. And I say that, nah, you really can't do that. That doesn't really make any sense. They're fundamentally different quantities, right? Mass is a physical thing. Area is not, for one thing, right? So they're really, really different things. Why would we ever believe that masses equal immediately and obviously to an area? Well, the argument that people actually make here, in fact, is kind of just a sloppy version of a Riemann sum, right? People will make the argument that, look, I can take this mass, distribute it across an interval, mass of a rod, for example, classic example, and chop that up into little pieces, and then look at each little piece, and on each little piece we have density times length, and then people say, well, visualize that density as being a height. What they're doing is they're literally creating a Riemann sum and then saying, and now visualize that Riemann sum as being an area. And if you take the Riemann sum out of that story, there is no argument. See what I'm saying? It's really, really important to have Riemann sums in the story. An area, once you realize that any connection you make to it goes through Riemann sums, becomes unnecessary. Is that cool? That makes sense to everybody? Okay. All right. So, very importantly, integrals are Riemann sums. Okay, so what we're going to try to do, we're going to try to kind of rip off that idea in a two-dimensional context. And just to repeat myself, in single variable calculus, this expression is what we're interested in. This is the object of interest. Forget areas. The useful geometric aid, I suppose, but this is what we're really interested in when we're doing single variable calculus, single variable integrals, because it represents taking an interval, chopping it up into little pieces, analyzing the question on the little pieces, and then just adding up to get the whole. So we're going to try to do something analogous. We're going to eventually develop this expression right here. We're going to walk through the details momentarily. But the purpose of this expression is so that I can take a now two-dimensional region like that, chop it up into little pieces, analyze the question on the little piece. I emphasize little pieces of area, not little pieces of length or width. Little pieces of area. Analyze the question on the little pieces of area and then add up over all of those little pieces of area. Okay, now there's going to be a couple of asterisks that y'all need to watch out for. These are going to be the same asterisks that, in fact, were always present when we were doing single variable calculus. On each little piece, we need to be able to answer whatever the question at hand is on each little piece by way of something that looks like this. If we're going to write down a Riemann sum expression, then each little piece we need to be looking at. It's got to be something times the length of that little piece. And let me say that a little bit differently. It's got to be something. I don't know what the something is. The something depends on the question. We'll deal with that as problems come up. But something times the size of that little piece. Right? So if you're interested in computing volume, then that something is height that you multiply by width to get area. If that something is mass, then this is going to be mass per unit length, aka length density, that you multiply by length to get mass. Okay, so likewise over here, whatever questions we ask over here, it's going to have to be the case that on each little piece, we're going to need to be talking about something times size. In this context, size being area. Right? So that's why we have delta x, delta y here. Details, of course, as to how you compute delta x and delta y. Chopping up the both the interval from a to b on the x-axis, likewise chopping up the interval from c to d on the y-axis. So, for example, if I want to compute mass in this piece is mass per unit area times area. And that makes sense, that works, the pieces fit. If this is the state of Colorado or Wyoming, take your pick, right? We'll broaden it to other states later on. Then I want to compute the population, let's say. How much population is there in this little, county, right? Well, population per unit area, otherwise known as population density, times area. And again, the pieces fit together, area cancels, right? It works. Okay, so not all questions have this feature. We can only answer questions that have this feature. Okay, here's the second one. And this one is another big deal. This also does not always apply. I need the whole to be the sum of the parts. Mass has this feature. If I take a one-dimensional metal rod, let's say, again, non-constant density, it has a certain mass. The total mass truly is, because this is how physics and mass works, the total mass is the sum of all these little pieces of mass that I chop it up into. Right? It just is. That's how mass works. That's the nature of the beast. Right? Likewise, area under a curve, the total area is the sum of the areas of those little slices of area. The whole is the sum of the parts. I like to summarize this as saying these are accumulating quantities, where the whole is the sum of the parts as you chop up your domain. So we're going to need that to be the case here as well, right? So I'm going to need whatever it is that I'm computing here to have this feature of accumulation. The whole of whatever it is needs to be the sum of all the little pieces that I look at on each little piece of sub-rectangle. And, well, again, thankfully mass has that feature. The whole is the sum of the parts. Population has this feature. The whole is the sum of the parts. And we just have to always make sure that, in fact, the thing we're trying to compute actually literally is the whole is the sum of the parts. Otherwise, again, crash and burn, the whole thing doesn't work. Okay. All right. So, this expression is going to be the thing that we use to answer a bunch of questions like this. It's going to be really important. We're going to do a lot of stuff with it, and that makes it worthy of having a name and a notation. The name that we give to this is it's a double integral. And we'll see why in a little while, what the motivation for that term is. For the moment, I can just say it's an integral where you're kind of looking in two different directions because it's an area, if you will. And we're going to use this notation, very standard. And why we use this notation, well, I think it's pretty believable. The whole point to multiplying delta x times delta y is it gives you a little piece of area. I think dA is a reasonable sort of shorthand to represent that. And then likewise, as is always the case, a limit of a sum, we use integral symbols. And we use two integral symbols here right next to each other. Very importantly, though, think of this, please, as being a single thing. This is not, as I'm writing it here, this is not a single variable integral of a single variable integral. Not at all. This is a single symbol. Think of this as the double integral symbol. And it represents a single summation in which you look at two separate indices and you add up over both of those indices. In other words, that you're adding up over the entire rectangle, not just in one direction. Okay. All right. Now, good news. The book does a bunch of stuff that y'all don't have to worry about. And this is not a bad thing that the book does this. The book uses something called irregular partitions, and they talk about arbitrary test points. If you want to do some real serious, Math 431, Math 531 kind of stuff, you need this. It is very important. In Math 219, we're not going to worry about it, and we don't need to, because in Math 219, we're going to focus on functions that are continuous. And when a function's continuous, these don't matter, right? Whether you use regular or irregular, whether you use the convenient test points or arbitrary test points, whatever. Doesn't make any difference for us. We're always going to get the same answer. And now again, there's really good value in this in other contexts. For anything we're going to do in this class and for any applications that y'all are going to see outside of this class, the functions in question are going to be either continuous or continuous practically everywhere. And you can just kind of chop up your domain into we're not going to need to worry about that kind of thing. Okay. All right. So just ignore everything the book says about this stuff. Okay, so let's see what we can do with this construction, this double integral construction, a 2-index Riemann sum construction. We're going to go back to the question of the volume. Whoopsie, I wanted this in yellow. The volume under a graph. All right, keep in mind a graph is like this. We've already computed the answer to this. It's not clear why we're going through the second time, but you'll see why in a couple of minutes. So how do we compute the volume under this graph? Specifically, the volume sitting over a certain rectangle. Like that. How are we going to compute that volume? And I argue that that volume, I can think of the whole of the volume as being a sum of a bunch of little pieces of volume. Let's see, I'll use blue. Oh, the blue looks like green there. Okay, let's see here. I will use orange. That would be nice. Okay, so a bunch of little pieces of volume. Now this is a geometric appeal. Right? You got to think about, what do you know about volume? What's the nature of volume? And I claim that if you, in the process of slicing up this rectangle into a bunch of little sub-rectangles, if you look at the volume sitting over each individual sub-rectangle, if you look at, in some sense, each little French fry, which is just, I don't know, that's what I see when I look at this picture, right? The volume of each individual French fry, if you add up the volumes of all of the French fries, you get the total French fry volume of your biggie fries. Does that make sense? Okay. Very convenient that volume has this property. Let me remind you, don't take it for granted. Not every question you might ask about this yellow solid has this accumulation feature. Now, just as a for example, something to be worried about. What if the question weren't about volume? What if the question were to compute the surface area of this thing? And now I ask rhetorically, is the surface area of this big yellow lump, is that equal to the sum of the surface areas of all the individual French fries? No, not at all, right? The individual French fries surface areas add up to way more surface area. Does that make sense? Okay. So not every question can be answered with a double integral. You always have to think it through and make sure that the quantity you're interested in has this feature of accumulation, that the whole is the sum of the parts. Anyway, heads up. Okay, next thing, is that volume equal to something times area? And why, yes, of course it is. Volume is height times the area of the base, so boom, no problem. Again, familiar high school geometry. Okay, fine. There's round off error, kind of, it's not technically, there's you have to kind of cut it, and there's a little bit of leftover, just like there is with single variable integrals, right? But in the limit, which is all we care about here, in the limit, that little bit at the top goes away. Does that make sense to everybody? All right. So, cool. We have now argued that volume can be computed with this formula. you will notice that this formula is exactly this right here, namely a double integral by definition, and so a double integral will compute this volume. Everybody happy? All right, so what was the point of this example? We already knew how to compute volume. I am going to skip over a theorem that I will come back to momentarily. I want to talk through it from the point of view of this diagram. This diagram represents what I'm going to call all of the players in the discussion we've been having and all of the sort of the connections that we've established between them. So very first thing, when we were talking about computing a volume, we established that you can turn a volume under a graph into an iterated integral. And then, earlier today, we said, well, hey, maybe if I want to compute a mass, and likewise any other application, I suppose, but let's stick with mass. If you want to compute a mass, it was tempting to say that we could turn that mass into an iterated integral. What we found is that didn't make any sense. The pieces just didn't fit together. It involved trying to understand mass per unit width or something. And I don't know what that is. I don't know how it works. And I don't know that it's an accumulated quantity. And there's a lot of other stuff I don't know about it. So there is no argument there. You cannot, what I've got X'd out in red there, you can't make that connection in an argument because it doesn't work. It doesn't fit. Okay. And I also made an analogous argument that you can't just directly relate mass to some geometric object without having some equivalent Riemann sum argument, which at the time we didn't. So I'm going to say you can't do that either. Okay, so this is where we were as of, 10 minutes ago. And now, this most recent thing we did, we defined a double integral, and we used a double integral to compute volume. Okay, so now what I want to do at this point, this being where we are, is ask what to do now. Why is this blue arrow relevant to us? And it goes as follows. It's because if I can compute volume with an iterated integral, and if I can just as well compute volume with a double integral, that means that these two totally different constructions, the first iterated integral being a single variable integral of a single variable integral, right? Single variable calculus of single variable calculus. And this new construction, structurally different. We're adding up over rectangles, right? Very different formula. But they both give answers to the same question. And that means that they're computationally, in terms of the result they get, the same. Said differently, it means this. It means that I can compute double integrals with iterated integrals. And that ends up being a really, really important step. Before I forget about it, let's come back up here real quick. I want to point out that's what this theorem says. If you have a double integral, you can compute it with, take your pick, either iterated integral. Okay. All right. So now we're actually in business at this point. And this is going to be our roadmap for how to solve problems, how to do applications, right? We want to compute some practical stuff. Y'all are largely, anyway, engineers, physicists, economists, etc. You want to compute one of these things? Step one is going to be turn your question, whatever your question is, write it as a double integral. I can't write it as an iterated integral. Not immediately anyway. But I can write it as a double integral. Step 2, cite big theorem that says double integrals can be computed with iterated integrals. Step 3, plug and chug. We know how to compute iterated integrals inside, out. When you're on the inside, the outside variable is a constant, right? There's this mechanical process for how to compute those things. So what we have is a roadmap for how to answer application questions. Step 1, step 2, step 3. That's how we're going to solve problems. Yes?
So we could indeed compute the the mass with a double or like an iterated integral? Like if we went back up.
Well, again, you have to distinguish between results and numerically accurate results versus meaningful arguments. And remember, that's what this class is about, right? It's not about the result. It's about whether your argument holds water. And if you directly claim that mass or whatever is an iterated integral, I don't know what you're talking about. That argument doesn't hold water. It just doesn't. It's really importantly missing a critical step, right? So what you have to do, you have to say, I want to compute population, and population I can write as a double integral, and that double integral I can then rewrite as an iterated integral. That's fine. That's the strategy. But this double integral is a really important step in that process. Does that make sense?
Yeah.
Okay. All right. Okay. So let me also point out while we're here, notice we now kind of volume has sort of served its purpose for us. Notice we're not going to be, let's see, I better leave that there. We're not going to be, let's see, I was using dark blue. We're not going to be doing this. You don't need to. I don't need to say, mass is a double integral. I can interpret double integral as a volume. Volume I can compute with an iterated integral. It's just not necessary. We got a theorem here now that says that volume doesn't need to be brought up, and I can just do this. So, pretty much, practically speaking, at this point, with volume having served its purpose, it doesn't really need to be thought about at all anymore. Everybody clear on what our strategy is going to be? Okay, let's do one. Here is one of those exact applications. We want to compute a mass where we have density describing how that mass is distributed over a rectangular sheet, like so. Here's our rectangular sheet. Density depends on both x and y. You cannot solve this question with single variable calculus. It doesn't work. But I can argue as follows. By the way, this example is very stretched out and way more than you need to actually write down in practice on an exam. When I'm done going through all the painfully, stretched out, fully detailed discussion, I'm going to talk specifically about what I need y'all to write on an exam for full credit. Right? But let me go through the gory details first, and then we'll come back to that. Okay, so here we go. Mass. The whole is the sum of the parts. I wanted to be in highlighter mode. Sorry. The whole is the sum of the parts. This is how mass works. Right? Mass is an accumulating quantity. On any individual little piece of my rectangle, mass is mass per unit area times area. That's kind of, you might take this fact here as a definition of what we mean by mass per unit area, right? And when mass is distributed over an area, that's what that density is. Okay. And then lastly, this, you'll note, is the definition of a double integral. Notice we have literally a Riemann sum here, 2-index Riemann sum, and that's our definition of a double integral. Okay, so we have rewritten our question. We have rewritten our question as a double integral. Now, let me clean up the mess here. That is step one in our strategy. All right. Let's see. Cheat sheet. Step two. Next thing I need to do, I need to rewrite a double integral as an iterated integral. All right. Cool. Boom. Theorem. No argument to be made. You don't have to talk about volumes and stuff. We have a theorem right here that says, yep, sure enough, double integral is iterated integral. Take your pick, whichever one you like. So, step two. Done. Yeah.
Why is it that we switched out, like you see in the top we have dx, dy, and then we have dy, dx in step 2?
Oh, it doesn't matter.
Just because it's rectangular.
Just kind of showing that I can do it either way.
Okay.
I wrote dx, delta x, delta y here because it doesn't matter and I felt like it.
Okay.
And then down here I wrote dy, dx because it doesn't matter and I felt like
Because
it.
it's rectangular, right?
Because what now?
Because it's rectangular, right? We could do that.
It's because area is both height times width and width times height.
Okay.
It just really doesn't matter.
Will it always not matter? The order the curve go?
There will be consequences in certain situations.
Okay.
Yeah, but you're free to do it either way, but there will be, one will be more desirable than the other in some circumstances.
Okay.
Yeah. In this case, it really doesn't matter.
Okay.
Yeah, right. You're happy?
Yeah.
Okay, is everybody good? All right, step 3 is computer iterated integral by plugging and chugging, and again, y'all already know how to do that. So I'm gonna, again, y'all know how to do that already. So 3-step process, and we're gonna get an answer, details to be worked out. Y'all can do that. Everybody see the big picture? All right, now a couple of things I want to talk about. I will eventually get to what's going to be required on an exam, but I want to talk about notation a little bit here. You'll notice that in the definition of an integral here, I just kind of rewrote delta x, delta y as dA, because after all of this right here, the double integral is just a shorthand, right? I mean, anytime you see a double integral, that is literally, by definition, just a shorthand for a Riemann sum. It's just a shorthand. It's just notation, right? Okay. All right. So, case can be made if I'm going to use this convenient shorthand at the end of this argument. Why can't I just use it kind of in the middle of the argument? So a lot of people sort of reason, and so in fact we do this, like this shorthand right here, that we use two integral symbols, the double integral symbol as a shorthand to represent the sort of the limit and the sigma part of the Riemann sum. Why can't I just go ahead and do that here, for example? Right? So perfectly reasonable, very common, and I support this. Instead of writing the clunky Riemann sum notation, go ahead and do yourself the favor of allowing yourself to write it with the convenient double integral shorthand notation. And this, keep in mind, when you see double integral dm, this is just a shorthand for saying that the mass is the limit of the summations of these little pieces of mass that I'll be approximating. It's just a shorthand notation, but isn't it nice? Isn't it more compact and convenient? Okay. So in practice, day in and day out, even though there's something weird about this, and the very first time I saw this, I got creeped out because I'm like, wait a minute, where's the m-axis? Right? It seemed weird to me. But it's not about an axis. It's just a shorthand for the fact that what I'm doing is I'm adding up a bunch of little pieces of mass. So perfectly reasonable. All right, okay, now, so the big question, which you've all been waiting for, what do I write down on the exam to get full credit? Right? And again, I do need to see all 3 steps in the process because, after all, this is not a class about answers. I don't care just about the answer. I need you to make an argument that holds water. Right? It's got to make sense. And so, as a doff of the cap to how important double integrals are in this argument, as a recognition of how this doesn't work, I need you to write down the double integral. And good news, it's so easy to do. It's really not that much to it, right? But I need you to write that down. So what you can do, full credit for the following, is to write that mass is a double integral of density times dA, which is an iterated integral, which you can then crank out with the fundamental theorem of calculus. notice this gives me the phase one, right? You've recognized that we're going to be using a double integral to turn an application into something we can get our hands on. Recognizes that the double integral is computed with an iterated integral, and then you crank out the iterated integral, of course, to get the number at the bottom of the page, and you put a box around. So this is all you have to actually write. Does that make sense to everybody? Okay. Now, for whatever it's worth, my own little personal, you don't have to do this, but this just makes me feel good. I tend to write this. I like to put in this little thing here. This is how, in my mind, I kind of get comfortable with that. Yeah, wait a second. Mass is an accumulating quantity, right? Let's make sure that what we're doing actually is we're going to make an accumulation argument about an accumulating quantity. You don't have to do that. For whatever it's worth, you're going to see me do it in all the solutions I'll be writing. Well, many of the solutions I write. And if you're curious why, that's why. Everybody on board? Yeah.
So in the diagram, when we skip the volume step,
Yeah.
is that because the Riemann sum already takes into account that it's a volume?
Yeah. In fact, to be fair about it, volume is not at all involved in our calculation. If the object in question to compute is mass, my answer will not involve volume in any way. So I argue that the whole is the sum of the parts with a double integral, right? So mass is a double integral. There's no volume in that case, right? Rewriting a double integral is an iterated integral. Now, how I know this is true, I like to justify from the point of view of volume, but I don't have to justify this every time. I've already justified it. We have a theorem that says double integral equals iterated integral. So volume doesn't come up here either. Does that make sense? I mean, again, it's underneath, I suppose. But in fact, a really rigorous argument as to why double integrals are iterated integrals doesn't involve volume at all. I like the volume argument because I can see it, I can get my hands on it. And I think y'all might find it easier to buy than the real rigorous argument that involves worrisome formalities about when can you switch the order of limits and nasty points of rigor that I don't want. I'd rather not get involved in if I don't have to, right? But yeah, so this to this, you don't have to cite volume, and of course the computation doesn't cite volume. So did I answer your question?
Yeah.
Okay, cool. All right. Okay, here's another example, the purpose of which is to talk about this convenient shorthand that is double integral notation. This is, you might call a kind of an intricate example of a practical problem, very real world. This problem occurred to me when they were building our house that I currently live in. And the front facade of the house has this kind of wall facade kind of a thing that's made out of stone. But the stone thickness is not a constant, right? The stone thickness varies in different places on the wall. So this is not exactly the specs of the wall on my house, but it was motivated by that. So here's the idea. We have this wall thing. You'll notice there's a rectangle, and I've got some kind of parameters that I've set up. I'm going to think of the y-axis as being up, and the x-axis as being kind of parallel to the wall, the base of the wall. And notice that density is highly non-constant, right? It's kind of it gets more dense the closer you get to the sort of the top right corner. It gets more and more dense. Yeah? Everybody with me? Okay. All right. More and more thick. Okay, so with that being the case, let's ask the question, how much work does it take to build this wall? Now, there's a lot of work that goes into building this wall, and you got to have the, I don't know, grout, or I don't know what that stuff's called, right? But whatever. But one of the things is, look, this is made out of stone, and each little stone has got some heft to it. It's on the ground, and you got to pick it up and put it where it goes. Some of the stones get picked up a substantial distance. Some of them don't have to go up very far at all. But all the stones have to get lifted by various different amounts. What's the total amount of work? Just the lifting, right? But what's that total amount of work that it takes to lift the stones to where they need to be in the wall? Does that make sense? Okay, so, well, the idea is, first, as promised, this is my little ritual. I like to start by writing that down. This is my recognition of the importance of the fact that the quantity I'm interested in, work in this case, is an accumulating quantity. The grand total amount of work indeed is the sum of the individual little pieces of work. Alrighty, so that being the case, let's look at this particular little stone right there. How much work did it take to lift that up to where it goes? And I make the case that that differential amount of work relates to, well, how heavy is that little stone? The differential amount of force, the weight, how much weight is there in that? And specifically, work equals force times distance. The distance for this little piece of stone at x comma y, the height that it has to be lifted is y. Okay. All right. By the way, that differential amount of weight, how much does it weigh? Well, I was given a density. I was given specifically that mass per unit area is that function, and, well, mass per unit area times area. I'm sorry, I committed a physics crime there. Weight per unit area, weight's not the same as mass, sorry about that. Weight per unit area, force per unit area, times area is what gives you force. Okay, and again, the force per unit area is given. And now, check it out. I have myself a double integral. All right, now I don't want to even consider how weird would this argument be if I tried to directly make some case that involved a single variable integral of a single variable integral. I don't even know how that would go down. But I have pretty conveniently, by just making simple references to, weight per unit area and work equals force times distance, no trouble at all rewritten this question as a double integral. That's fine. Having done that, I can then cite, as sort of phase 2 of the argument, cite that my double integral can be rewritten as an iterated integral. No problem. And then phase 3 would be the ugly details of kind of how to, crank all that out, and that's just details. Y'all can check me on that, make sure I got it right, and that's the final answer. Is everybody okay with that? Yeah.
So how did you know you had to split up the really small dw into y and df? Why not the other way around?
Well, you just have to you have to think about what tools do you have at your disposal at each stage along the line, right? And so work. Could I have written work immediately as work per unit area times area? I wasn't given work per unit area, so I can't do that. I mean, in theory, if I had been given such a formula, I suppose I could, but I wasn't, so I can't. And so I have to ask myself, what do I have that actually addresses a little piece of work? And the only thing I have is that work is equal to force times distance, so I wrote that down. And then I ask, okay, I've taken a step. What about weight? Do I have any do I know weight per unit area? And conveniently, yes, I did. And so I was able to kind of connect the dots. But you just have to, write down what you can and hope that you can eventually get it down to a double integral, like I did here. Okay, this is a pretty good place to draw the line. We'll draw the line right here for today. Good to see y'all, and see you on Friday. Have a good rest of your week. Let's see here. And reminder, of course, if I didn't get you marked down for attendance, make sure you get marked down.